Okay, so linear filters in general, since they will always leverage the Fourier domain, whether we apply these filters specifically in the Fourier domain or we actually do space domain convolution, either way they're manipulating what we understand of the Fourier properties, okay? So as a result, linear filters by definition will have certain properties, and we want to understand what those properties are, and if those properties are good enough for the kind of tasks or kind of operations we may wish to perform on any given image. Okay? So we'll try to understand that. But in general, anytime we talk about a linear system, right, a linear filter is nothing but a linear system. A linear system has its characterization. Okay? So if I talk about an input signal, in this case an image, and we say that we're going to actually apply a digital filter to it, linear filter in this case, the actual specific operation that we are performing is a linear convolution. Okay, so the result of applying this filter on an image is actually just linear convolution, which we already saw last time. Okay, so any filtering system, linear filtering system, can be thought of as a convolution operation. Okay, and the overall linear system is characterized by what is called the characterization properties of the linear filter itself, right? So what does a linear filter actually do? We can understand that in order to characterize the overall linear system. And we'll look at that in a second. Now, anytime we talk about filtering on an image, there are certain properties that we wish to have for filters that we design. Okay? If I think of any image, what do we desire from an image, right? We wish to have low noise, right? Good visual contrast. Now, when you think of those are qualitative properties that we are typically expressing for an image. What does that translate to in terms of frequency properties in an image? Okay. So when I say I want low noise, what does that mean? Sorry? Very good. So when I say low noise, I do not want a lot of high frequencies, right? Random high frequencies that are present in the image. Okay. Now, when we say I want good visual contrast, what does that mean? Sorry? It means I want high frequencies in my image. Okay? So keep in mind, when we translate these qualitative aspects of what we find interesting or appealing in visually looking at an image, may not directly translate in things that are coherent in the frequency domain, right? The fact that on one hand we want to reduce high frequencies, on the other hand I want to accentuate high frequencies, right? I mean, those are sort of conflicting goals. Nonetheless, that's what we wish to get from an image, right? And now the question is, how do we design filters that give us those properties? Okay. Anytime we talk about a filter or an operation on an image, there are certain qualitative properties that we are looking for an image. Eventually, we have to translate those qualitative properties into something quantitative, right? We have to be able to express what we want quantitatively so that we can actually come up with an operation, in this case a filter, that can get us those properties. So we want to understand what's qualitative and how we translate that into something quantitative. So smoothing, right? When we talk about lowering the noise, what we are actually looking for is smoothing, right? So when I talk about a signal, if you think of a one-dimensional signal, right? Let's say you're looking at a scene which has a fairly gradual variation in intensity, right? Now, a good gradual variation in intensity basically should be representative of, let's say, changes that are somewhat linear. Right? Now, this would be the ideal variation in intensity going from, let's say, low to some high intensity. If I have something like this, this would appear to be fairly gradual change. Okay. Now, if I corrupt this with noise, right, I would tend to see spurious spikes come up from time to time, right? So obviously I don't have a nice gradual change anymore. Now in this case, this is an extreme situation, right? If I think of my noise model as this additive zero mean ergodic noise that we have thought about before, then of course I should see simply some spikes come up every once in a while. Right? Now if I want to get rid of noise, well, I would expect that somehow I should be able to get rid of all these spikes and come back to this original line that I have, right? And I can do that by essentially smoothing operation. Right? So anytime we think of smoothing, it is nothing but a way for us to remove noise. Right? So when we want to reduce noise, we typically think of that as a smoothing property that we wish to get out of an image. Now the other thing that we want is what is called deblurring. Okay. Now how do we express deblurring, right? So let's say, we have a very simple edge in an image, right? A very nice contrast change. So you have two areas in an image, both with constant intensities, but they're different. So right at the transition point of those two areas, what would we expect our signal to look like? I would expect our signal to look something like this. Would you agree? So everything here has one intensity value, right? Let's call it I1 and this is I2. Right? So two separate intensity values. Now this would be nice, right? If we had this, we would have a very nice transition between the two regions, and what you would call that, when you look at it, is a very nice contrast. Now, on the other hand, if I give you a signal which looks like that, okay, the question is now, where is my transition point? What is the particular point at which the two regions are truly separate? Hard to tell. Could be here, could be here, could be in between, somewhere. But what this becomes then is that, yeah, I can clearly say that this is I1, this is I2. But everything in here, I don't know, some blend between I1 and I2. So as a result, this region is what you would call blurred region. You would not have the clarity of where exactly the transition is happening. Now this is blurred, and one of the things we want to do on images in order to improve its visual quality is to de-blur this. I want to actually change this kind of a signal and bring it back into a step signal. So this would be de-blurring. Another property that we want to have in our image. Now sharpening is pretty much the same. Okay? Sharpening is the same thing as de-blurring. And of course, we could potentially be looking for a combination of all of these. I may have an image which is noisy and blurred together. So these are some very specific goals that we want to achieve by performing some operation on an image. Now we can do all of this by filtering an image, and we'll specifically see what linear filters get us. But before we do that, let's talk about linear filters and how we characterize linear filters. Right? So we said in our simple sort of process diagram that H would be our linear filter. Now I wish to characterize a particular linear filter. The way you do that is by looking at the unit pulse response of that filter. Okay, or we can certainly look at the frequency response of a filter. So what is the unit pulse response of a filter? It's very simple. If I have a filter H, and if I subject the filter to a input signal which is a unit pulse, whatever I get out is the unit pulse response of the filter. Okay? And in fact, I can characterize all the properties of the linear filter simply by understanding its unit pulse response. Now, this is analogous to actually characterize the filter by its frequency response, okay, which would be nothing but looking at the response in the Fourier domain. Okay. Now, remember, we can design filters either in space domain or in frequency domain, right? It's the same, they are linear transforms, so they're invertible. So it doesn't matter which domain I design a filter in. The choice is really dependent on in which domain can we express the properties of the filter that we wish to design. Okay? If I say that, well, you know, what I want to do is design a filter which attenuates all frequencies greater than 4 cycles per image. Okay. If I give you properties of the filter in those terms, what would you do? Where would you design the filter? In Fourier domain or in space domain? Fourier domain, right? It would be easier for us to look at the Fourier domain and say, okay, now it's very easy for me to come up with a filter for that particular domain. Of course, if I wish to apply that filter, I may not wish to actually do that application in the Fourier domain. So what you would do is design the filter in the Fourier domain, take its inverse Fourier transform, inverse DFT, and then say, okay, this is my space domain filter. And I would convolve that with my image using linear convolution. Okay? And the resultant I would get would be my filtered image. So oftentimes we end up designing filters in the Fourier domain, taking its inverse Fourier transforms and applying them as linear convolutions, not necessarily applying the filtering operation in Fourier domain. Okay. Now, the frequency response of any filter that we design is nothing but the filter's DFT. Right? So I have a filter H, I take its DFT, and immediately what I would get is, of course, H tilde, right? H tilde will have a certain magnitude and a phase. And that's exactly what that filter does. It will modify the input image's frequency by the magnitude expressed here, and it will alter the phase according to the phase expressed here, right? Because remember, in the Fourier domain, this operation is nothing but pixel-wise or index-wise multiplication, right? So we can think of this and look at it in terms of an example if we want, right? A very simple signal, let's say we have a cosine image going in, okay? If I have a cosine image going in and basically I convolve that with my filter H, what would I expect to get? Right? Well, we can write out the convolution. We know what the convolution is. Right? We can solve for all of this, and all you would find, right, is that, remember, your cosine signal is now modulated by the magnitude given by your filter's magnitude, and the phase is shifted according to the phase of the filter. So you can work through this, you can see what it comes down to, and that's all it does, right? It basically modulates it by the magnitude and shifts it by the phase of the filter. Now the unit pulse response, if you want to characterize this filter in the space domain, well, all we have to do is understand what happens to a unit pulse that is sent to the filter. Okay? So now we have to think of our image as being a unit pulse. So I can certainly express my image as a unit pulse, right? If I express the image as a unit pulse, it would be a delta function where it will take a value of 1 when I and j are equal to 0, right? Otherwise it's 0. That's it. Now if I convolve my image with my filter, what will I get? Well, what do we end up? All we get is sorry? Very good. All I get is h of ij, right? So what does this tell us? That if I have a unit pulse going in and I convolve it with my filter, all I get is the characteristic response of the filter at the location ij. Okay. So another way to characterize a filter. Now of course, as we said, you know, I need to design a filter to get the qualitative properties that we have talked about, right? Smoothing, sharpening, deblurring, or some combination thereof. We can do this in the frequency domain, like we said, right? And of course, in that case, we would express things in the continuous space, right? Or we can look at the analogous version in the space domain. There are certain filters that obviously are very useful. Now, we talked about this briefly last time, which is I can design ideal filters. Right? I can design ideal filters in the frequency domain where I have very strict criteria that I can impose, right? I can say that what I want is basically a cutoff at a certain frequency in the frequency domain. So like I said, let's say I have an image, right, which is a 100 by 100 image, okay? And I want to operate on this image with a filter whose properties are that it cuts off all frequencies greater than, let's say, 25 cycles per image. Okay. So, well, that would be an easy filter for it to design, right? All I would need is to say that, well, in the Fourier domain, give me an isotropic filter, right, a circle, so that it basically cuts off frequencies equally in all directions. So I need to come up with a mask which takes a value inside the circle where I can say R has to be equal to 25, right? So I need the radius of this guy to be 25 and it has to have a constant value. Okay. So this would be an easy filter to come up with. All I have to now decide is what value does this thing take. So what I want to do is just simply remove all frequencies greater than 25 cycles per image in my image, then I can do this kind of a filter. And if I set all the values here to be 1, everything else to be 0, then what will happen? I will not change the magnitude of any frequencies that I'm retaining, right? They will all just be the same. Now if I choose to have a value different than 1, then you are affecting the magnitude of the frequencies that we are keeping in that image. Right? Now is there a tremendous utility in altering the magnitude of the frequencies that we retain in an image? Let's say I set this value to be 10. What will that do? Okay, let's start the other way around, right? If I set the value to 0, what does it do? Okay, very good. If I set it to 1, what does it do? Okay. If I set it to 10, what happens? So 0, magnitudes go away. 1, they stay as they are. 10, what happens? Sorry? Higher contrast. What does that mean though? Remember, I mean, higher contrast is great, right? We look at something and we're not quantitatively defined what contrast is, right? It's a visual property that we expect. And what does higher contrast mean for us? Very good. So greater variation is what? In terms of intensities, it's the difference, right? So going from one pixel to the other, I have a larger change in the intensity value. Okay? So by setting this value greater than 1, what are we doing? We are widening the difference, right? Now, is that useful? Do you think that's useful? Mm-hmm. All right, so very good. So what we are saying is that this is really what is going to happen to that step edge, right? Assume that I have my step edge. I'm sorry, my little nice smooth function here. Assuming that this everything here, all the intensity values that are present there, fall within this domain. Okay, everything will have a value that becomes larger, right? So I would end up with something like that. Have I changed anything? Yeah, I've changed the values, absolutely. Does that have any meaning though for me? In terms of information, remember, when we work on images, right, we are working in a predefined domain. Right? We are working in a quantized space that we have set up, right, in the digital version. I'm the one who decided this is 0 and this is 255 for an 8-bit image. Okay. By doing this operation, let's say the actual matrix that you end up with goes from 100 to 1000. What am I going to do with that? Right? If I want to visualize that, it doesn't matter what it is, I'm eventually going to map it back to what I'm going to use to visualize that space, right? So I have to somehow come back and say, okay, great, I get all my values back for the filtering operation. All the values are now in the range of 100 to 1000. Well, great, but I have to scale everything back to 0 to 55 so I can actually visualize it. Right? So from a visual perspective, it really doesn't change things a whole lot. Now, certainly if some of these pixels or intensities there were getting contributed from frequencies we eradicate, while others were coming from frequencies that we retain, then you're right? We will see a better differentiation as long as we somehow remain within this range. Right? But that's a very, very unpredictable thing. It's very hard to control that property. So as a result, you know, having values that are arbitrarily set for frequency that we retain is not a very useful thing. We don't do it often because we don't know exactly how that will affect things. Furthermore, at the end of every inverse Fourier transform operation, we are going to rescale our images and the matrix back to bring it into a working range of values. So as a result, these kind of things are less helpful. Okay. Someone had a question? All right. Okay, very good. So, again, as I said, if we do this, this would be a very simple filter design, right? And if we come up with any specification where we say the filter takes a certain value within a range that we specify, okay, cutoff given by u and v, and it is centered, then of course we end up with an isotropic filter because we know what these frequencies mean for us, right? And this is, I'm sorry, when I say centered, it's centered on a Fourier domain which is centered as well, right? So this would be the 0, 0 of the Fourier domain. This would be 50, 50, okay, for a 100 by 100 image. Okay, so this is in the centered DFT, not the non-centered. Now, does everyone understand? I keep saying isotropic. Does one understand what isotropic means, right? Okay, so isotropic means is that we are designing a filter that affects every frequency independent, with a specific specification in terms of cycles per image, independent of the orientation of that frequency. Remember, we are working in a multidimensional plot space, right? So we have a propagation direction as well. Okay. So if I were to replace this guy, okay. So if I design a filter which is a square, right, of length 25. Now this is great, right? So I have a cutoff of u, right, and a cutoff of v, right, where u and v cutoff is 25. Right? Would you agree? This is the filter that I just put together. But this would not be an isotropic filter. Okay? This would not be an isotropic filter because if I think of frequencies that are propagating, let's say diagonally, right? So if I have a frequency propagating in this direction, this length obviously is not 25, right? So the cutoff here is what? Yeah. Right? Right, so it would be 12.5 squared, so each one squared added and taken the root of, right? Okay. So this is not going to be 25. So the frequencies that are propagating not horizontally or vertically will not have a cutoff at what we wanted. So in fact, it is not an isotropic filter. An isotropic filter simply means that all directions get the same property of the filter. All frequency orientations are affected similarly. So obviously in a two-dimensional space, if we want an isotropic filter, it typically has to be something that's circularly symmetric. Okay. So circle is an isotropic filter, square would not be. All right, now the most common set of filters that we design, since we are designing them based on understanding of altering frequencies, would be what we call low pass filters, high pass filters, and of course what we call band pass filters, which are really mid-pass frequency filters, right? And we've already seen examples of this, right? When we were talking about masks, we would come up with, we talked about 3 types of masks: a low pass, a band pass, and a high pass mask. Okay? So those are typically the 3 kinds of filters we design as linear filters. What would be the general use of these kind of filters? One, if we have low pass filters, what are the properties that we expect from low pass filters? Very good. To keep the low frequencies, so it's going to remove all the high frequencies, right? So potentially noise, it's going to reduce noise. Any low pass filter will reduce noise. But what is it going to do to high frequencies that are not noise? It's going to blur them, right? Because basically, like we said, if I truly have a nice contrast, like a step signal in my image, well, it's going to make this guy look like that, right? Because it's going to remove high frequencies, the spike here, and it will appear as if it's smoothed out. It's going to blur. Okay. So that's what a low pass filter will do for us. Now a high pass filter, on the other hand, is removing all the low frequencies, right? So if it removes a lot of the low frequencies, it will actually enhance the details that are present, right? So it accentuates the high frequency that we have. So as a result, it would actually remove blur, right, and enhance the contrast in an image. But of course, if there is noise in the image, it will bring out all the noise, right? Because it's not that it's bringing out all the noise, it's actually, the noise becomes much more prominent because we are retaining all the noise but removing the low frequencies. So smooth things go away and the spikes remain. Okay? The image starts looking very noisy. Now band pass filters are generally very specialized filters, and the generic band pass filters are not something that are pre-designed and used. They tend to be very application specific, because in order to design band pass filters, which means we want to retain some middle range of frequencies, we need to know what that mid range is. It's very difficult to design a generic filter without understanding what frequencies we want to retain. Okay? So band pass filters tend to be very specialized. Now it's a great example of a low pass filter. We've already seen one, right? A perfect nice little circle as a mask. But a excellent low pass filter is a Gaussian filter. And we kind of talked about this a little bit, right? Why a Gaussian is a good low pass filter. A Gaussian in general, in both spaces, remains a Gaussian, right? And as a result, doesn't have artifacts that it creates in either domain. Right? I design a Gaussian in space, it's not going to end up as a sink, right, in my Fourier domain, and vice versa. So it has nice smooth properties, right, and it's very easy for us to actually design a Gaussian filter. Remember, the Gaussian is expressed simply by a couple parameters, right? So I can write the Gaussian in frequency domain as simply being an exponential of minus 2 pi squared sigma squared, and then of course the frequency. So it's a two-dimensional, so omega sub x squared plus omega sub y squared. Now, of course, in the digital version, all I have to do is divide it by n squared in order to normalize the size, right? Remember, a Gaussian is what? It's a continuous function. What is the integral of the Gaussian? Sorry? Very good, right? So the integral of a Gaussian is 1. Of course, that is true for continuous functions, right? Because the energy under the entire Gaussian curve is always 1. Okay? Now when I convert it into the digital version, I have to divide it by n squared so that all I'm doing is ensuring that the energy under the defined Gaussian still remains 1. Okay? That is the reason you always will have a division factor in order to ensure that the integral remains 1. Okay? Now, if I plot this out, right, as a one-dimensional plot, you can see that for a sigma equal to 1, this is the kind of function I get. For sigma equal to 1.5, I get narrowing. Okay? So what that means is that this is a frequency domain, right? Larger the sigma, narrower is the low frequency cutoff, right? So larger my sigma, the narrower this gets. Remember, this is centered at 0, right, which is basically where my low frequencies are. So if this width gets narrower and narrower, then I'm eradicating more and more of the high frequencies, right, because they are getting closer and closer to 0. Okay. Lower the sigma, the more of low frequencies that I keep. Okay. So this becomes a great low pass filter, right, because basically it's retaining all the low frequencies. The amount of low frequencies we retain is simply dependent on sigma. Okay. Okay. Now a band pass filter basically is something that removes high frequencies and low frequencies, right? So a typical band pass would look something like this, right? 0 coefficient, or 0 weightage around frequencies that are 0, and of course 0 weightage around frequencies that are high. Everything in between we want to retain. Well, so a simple band pass would be a shifted, sort of two Gaussians, one shifted by the other. Okay. So I can design a band pass filter simply by combining two Gaussians, right? So I can write out a band pass as being this in the Fourier domain, right? The first one is just a simple Gaussian. The second one is K as a constant multiplicator to the sigma on the Gaussian, right? And then I subtracted the two. I would end up with a band pass filter. A filter that you design this way is basically called a DOG filter, or a difference of Gaussian filter. Okay. And it will have this particular shape. A high pass filter, on the other hand, would be something which is kind of an inverse of a Gaussian. Okay? So it should take values of 0 around the low frequencies and values of 1 certainly at the high frequencies. Right? So a simple function that expresses a filter like this would be a Laplacian. And of course, again, we can express this filter as a u squared plus v squared, again divided by n squared. Okay, we want all the coefficients to sum up to 1, so you want the integral to come out to be 1. Okay. So if I look at this, this would be a Laplacian, right? And Laplacian is again nothing but a second order partial derivative that we can take of a function. So this kind of a shape would give us a high pass filter. So the most common band pass filter, like I said, it's not something that we use very often, but the most common filters that we use are going to be Gaussians for low pass and Laplacians for high pass. Now, a few classes back, right, we talked about sort of this notion of combining multiple images in order to reduce noise, right? So when we did that operation, what were we doing? We were basically smoothing, right? We were removing noise by smoothing, and the idea was that, well, if I keep adding up the same the intensity values at the same position in my image multiple times, then I would reduce noise. Right? So we were doing averaging of the intensities, yes? Now can I do averaging in just space domain, single image, right? But think of average as a low pass filter. Can we do that? Very good. If I can do that, what would my filter look like? A Gaussian filter. Why? Right. But is averaging the same as Gaussian filtering? So if I say that, we're talking about filters, right? And we are describing them right? We're writing out our filters like this, and we said, well, a Gaussian, all right, is a function that takes this shape, right? Now, we've talked about using average, the notion of just doing averaging as a low pass filter also, right? Because it removes noise. So what would the average be? What would it look like in my frequency domain? Very good. So, would you agree? An average is a filter which would look like this, a perfect ideal filter, right, a hat filter if you will. An average will have a width of m and the magnitude will be 1 divided by m. Would you agree that this is an average filter? So this is an average filter in the frequency domain. Okay? This is the average filter in the frequency domain. what we talked about is an example of doing, when we talked about averaging, is we are actually applying this kind of a function in space domain. Okay. So in the Fourier domain, what you end up with is a sinc function. Okay. In the Fourier domain, an average filter in space would be a sinc function. But this is the general shape of the filter that we are talking about when we talk about an average filter. Okay. And the reason we end up getting low-pass filtering properties is because of the fact that dominant amount of energy retained, right, all the coefficients or the intensities retained are coming from the frequencies that are contributing in the low region, and the high regions are getting attenuated. Okay. So the high regions get closer and closer to zero. Now, as we said, all of these filters have very, very specific properties. We have actually talked about low-pass filters, high-pass filters, right? But in a way, when we talk about improving the quality or the properties of an image, a lot of times, well, they are contradictory in terms of what we want, and more often than not, images tend to be corrupted with noise. Okay, so we never talk about an image which is noise free, because there are various reasons why noise is going to propagate into the image. Right, some of we talked about, and more often than not, we can think of noise as being an additive noise corruption in the image, right? A model that we have seen before, where we said that, the image I have that I actually capture is the ideal version of an image plus a noise signal, right? So this would be an additive noise model for image acquisition or image generation, and then the other one is a multiplication where the addition is replaced by a multiplication. Right? So there are two kinds of dominant noise models. The question is, when we do these filtering on images, for real images, our images are composed of this model. So what does it do to each of the terms? Right? So we want to understand what are the properties of our filters with respect to each portion of the signal. Because as much as we want to improve the image, we also want to understand its impact on noise. Okay? So of course we can come back and say, well, let me figure out what my noise properties are. What is the property of the signal? And we can go back to what we have seen before. If I say it's additive white noise, well, okay, I can assume it is zero mean. It's an ergodic signal. So we know what the properties of that are, right? So as long as I take a very large number of samples, the mean of n should go to 0. Okay? So we know what the zero mean noise model can be. Now, I want to understand, since we are talking about linear filters, right? And everything that we know about linear filters, we know it affects the frequencies of the signal. So if I want to know how my filters will affect the noise, I want to look at the noise in the frequency domain. Right? So what is the Fourier domain or Fourier spectra of noise? Okay. I just expressed what noise is. It's a zero mean ergodic signal. Right? So it's a random signal which has a zero mean. What is its Fourier domain going to be? What Fourier spectra are going to look like? So I want to know that. Well, great. So if I had n, that's easy, right? I can take the DFT of n and I would be able to see what its Fourier spectrum looks like. Well, I don't really have n, but as a result, well, one thing I do know is that the signal is zero mean, right? So what does that mean? If I have a zero mean signal, then I should expect that the mean of the magnitude in the Fourier domain should be a constant, right? It should be a constant. So what that means is if I take the Fourier transform of my noise signal, look at its magnitude, the mean of that is going to approach some constant value, eta, okay, where m, of course, number of samples I have in my signal is well, infinity. So what this means is that I can't really look at the Fourier spectra of my noise signal, but what I can say is that on average, the Fourier spectrum of my noise is going to be relatively flat. Okay. So if I,
Why is that if the noise has this specification in the image, then in the Fourier domain, what is the reason for the conclusion that we made in this?
so very good. So what is this? Let's think of a ergodic mean noise signal. Okay. So what should my noise signal look like? If I were to sample, right? Let's say I'm sampling over some axis, right? Let's call it time domain. Okay. I know I have some underlying distribution, right? A function from which noise is coming. And I know the mean of that is 0. Okay. So what, let's say, think of a good example of a function I can use which we have as a mean of 0. Very good. Right. So let's say for now that I'm going to use a nice little Gaussian as my example distribution which has a mean of 0. Okay. Now, I'm going to sample values from this. Okay. So I end up, as I go along, a bunch of samples. Some of them will be high, some low, some mid-range. Okay. So I keep sampling this to infinity. Okay. So obviously I end up with some function. The mean of this distribution is this. Okay. Now if I were to take the Fourier transform of the signal, I would find that, well, it generally has a Fourier plot. Okay. So let's say this is U. It's going to basically be something which is relatively flat, but of course it's going to have variations. Okay. It's going to have variations, but it's going to be relatively flat around something we call eta. Okay. Because in general, it's going to have sufficient number of samples at all possible frequencies. So the number of occurrences of each type of noise I draw is going to be something that's centered around this, right? Whether it's low or high. Okay. So remember, because it's random, the chances of drawing a sample from this end and then drawing another sample from this end is about the same, right? So the probability of draw here and the probability of draw is the same. Okay. So I can actually be drawing samples that are very far separated, which would be very high frequencies, right? That probability is just about the same as drawing samples that are very, very close to each other. So I have the same chance of drawing samples that represent high frequency variations as the chance of drawing samples that represent low frequency variations. And that's the reason why in the Fourier domain, the spectrum of it, well, it's going to vary a little bit, but the mean of that spectrum is going to be constant. But this is an interesting meaning for us, right? What does it mean? It tells us that the noise that we have in our image is across the full spread of frequencies. It's not just high frequency noise. There is low frequency noise also in our images. Okay. when we see a spectrum like this generally is called white noise. Okay? We refer to this as white noise, where eta becomes the power of the noise. Okay? White noise simply means that the noise is coming from the entire spread, the entire range of frequencies that we are working over. So, if this is my noise signal, then I can start understanding how my filters will affect my noise as well. So let's say we have our image, right? The image is going to have some signal, some distribution of frequencies. I have my noise, which is going to have a spectrum that looks like that, right? Spread across all frequencies. Of course, if I look at their corresponding Fourier domains, remember, an image is generally, it's always band limited, we know that. But also, we know that it will always have larger energy in the low frequencies than in the high frequencies, right? So most images will have some Fourier distribution that looks like this. And of course, the noise, we know it's going to be somewhat constant, okay? Which means if I now design a low-pass filter that I design is invariably going to need to have a property which is qualitative along these lines, right? It needs to remove high frequencies but retain all the low frequencies. Right? So if I design a low-pass filter which has this kind of a shape, then what will it do to my image, right? Sorry, let's go back here. What will it do to my image? It will retain obviously all the low frequencies, get rid of high frequencies. Same thing for noise, right? It will get rid of high frequencies, but the low frequency noise will still be present. Right? You cannot get rid of that. Is everyone okay with that? So this is a trade-off, right, when we talk about linear filters, because they linearly affect frequencies. Well, when we have a combination of frequencies coming from image data and noise data, we have to retain both. Right? We cannot eradicate one while keeping the other. So we will end up preserving all the low frequency noise along with low frequency information in the image as well. Okay. Now, of course, we can look at all of this in the digital domain, right? So we know our digital white noise model. We've sort of seen it before. J equals I plus N. N is digital white noise, which means that on average, as long as we have sufficient elements of N, the average will be 0. Now, you looked at averaging as a filter, right, in the past, as a smoothing filter to get rid of noise. And we can actually look at averaging in the space domain, okay, to get rid of noise as well. So, remember, noise is ergodic, right, which means that it doesn't have any dependency on the spatial position. So if I were to have an image, okay, if this is my image, right, I have a particular intensity value here, okay, in my image, not my noise, in my image. And I say, what is the intensity value going to be over here? Okay. Do you think the intensity value here has any relationship with this guy? Very good. There is, right? It's an obvious relationship between the intensities at the two locations. The reason is because, well, these intensities are coming from a visual scene, a visual space which is continuous, right? So unless and until there was a large difference in the scene, real scene, exactly at this location, these two should have a relationship between them. Right? Now, on the other hand, if this was my noise image, would these two have any relationships? No, because each pixel, the noise is randomly sampled, right? Independently sampled. So as a result, they have no relationship with each other. So what does that mean if I were to now, in the past what we did was we said, well, I have, 1,000 of these images, and I'm going to do smoothing by taking, right, all the pixels at this location. So all the pixels along this particular location, I'm going to average them all, right? That's what we kind of talked about when we said multiple image averaging. Now that worked out great because the noise at every one of these locations is independent, right? But the intensity is not. The intensity is, if it's coming from the same scene, we expect it to remain the same. Right? So that's kind of what brought us the benefit of averaging. Now, if I were to forget this and say, well, can I do this in space? Right? Can I average 1,000,000 pixels in space and expect to get the benefit of noise reduction, smoothing of noise? Well, makes sense, right? I mean, whether the noise is sampled independently this way or independently this way, the noise is just this noise, right? I should get the same benefit. But of course, the problem is that across space, I can't expect my intensity to be constant, right? But what can I expect? Maybe not constant over 1,000,000 pixels, but in very small spatial regions, I can expect the intensity not to change too much. I can't expect it to be the same, but I expect it not to change too much. Would you agree? Of course, yes. Then there's a problem, right? So we can think of these properties that we expect from an image, and based on that we can think of doing averaging in order to remove noise, or more specifically get smoothing properties in the space domain. Right? So I can take a small set of pixels and say, let me average all of them, and if I do that, right, just like we've done with windowed operations in the past, I can alter the pixel value at the center of this region, and I say, well, I expect the noise to be lowered because of this averaging operation under the model where noise is additive and is IID sampled ergodic noise with zero mean. Right? So we can actually come up with an average filter of some size m by m, let's say a 3 by 3 as an example, and we can actually do windowed operation, and this would actually give us smoothing, reduction in noise. Of course, smoothing comes with the opposite properties like we have seen, right? Just like any low pass filter gives us reduction in noise but will blur the image as well, so this does the same thing. Right? So as a result, average is another low pass filter that we very commonly use in an image, and it comes from these properties. Okay? Now, if I really want to leverage the fact that this is IID ergodic noise, zero mean, what would I want to do? I would want to average a larger number of samples. How do I do that? No, but I don't have multiple images, right? I want to, sorry? Very good. So I can make m by m larger. So m can be a larger value. So instead of 3 by 3, I go 5 by 5, I end up with 25 values that I average. A 7 by 7, 49, 9 by 9, 11 by 11, odd numbers, remember, right? So I can make it larger and larger, and I will keep reducing noise. Of course, I have a problem with this as well, right? What is the problem here? I'm smoothing my image more and more. Okay. Now, why is that? Very good. So obviously, it's very easy to understand, right? We are doing this. I'm going to take a whole bunch of values. As I get larger and larger, they're not even related to each other, right? But I'm going to average them all together. I'm going to expect a lot of blurring, right? Things are not even going to look anymore like what they appear, right? Because I'm going to average, right? I mean, the chair, the carpet, someone sitting on the other end of the room, I'm going to blend all the colors together and replace a color, right? So it doesn't even appear anymore like it used to. But remember, now we are doing this windowing, averaging, right? What is the actual operation we are performing? Let's say we take a 3 by 3. Okay. Now, in order to perform averaging, all I'm doing is a sum, right, of, let's call this M, right, M by M, so 3 by 3. So I'm doing a sum over 3 by 3 of, let's call this W, okay, W weighting, right, with my image, right, at the same location. This is what we are doing. Would you agree? So this is in general what we are doing. But do I need this guy here? What is this? This is a windowing operation that kind of you've seen before, right, when we talked about binary images. Can I start expressing these as specific values? I can, right? If I want to not have this guy here, can I give each one of these a value? In which case the result that I have is nothing but the weighted sum of this with the elements of the image. Right? That's all. That's what averaging is. Okay. Would you agree? Very good. Now, since this is my averaging operation, if I wanted to show it as an image, right, of the same size as n by n, okay, what would this guy look like? This is my 3 by 3, right? Here. It has values 1 by 9. Right? Everything else is 0, right? I mean, I can take these two, this image and the other image, overlay them, and I can take a weighted sum of the entire two things. Would you agree? Yes? Now, if these are my weights, and this is my image, can I write this weighted averaging operation as a convolution operation? Certainly I can, right? All I would do is flip this guy, flip that guy, shift it to any position I want, and take the sum, the linear convolution, right? I can do this. So basically, by doing this is nothing but a linear filter, isn't it? So if I can write it as a linear convolution, I can certainly express it in the Fourier space. The question is, what is this going to look like in Fourier space? You already know the answer to this, right? It's going to be a sinc function in Fourier space. Very good. So, and the fun part is, if you sit down and think of it, so in the Fourier space now, well, okay, not 2D, sorry, hard to draw, 1D, okay, this thing is going to look like a nice little sinc function, so 0, okay. Now, remember we did this for a 3 by 3, okay. If I go to a 5 by 5, is that 5 by 5? Yeah. Okay, if I go to a 5 by 5, it's still a sinc function. What's the difference? Sorry? Amplitude, of course, you know, this is all going to be 1 by 25 now. Okay, what else? Huh? Sorry? The width of this sinc function. Okay. So what happens? As this guy gets larger, this guy gets narrower. Okay? So if this guy gets narrower, basically what happens? I remove more noise, more high frequencies are lost, right? So of course I reduce more noise, but because more high frequencies are lost, more blurring happens, okay? So that's basically the trade-off we are working with, right? By increasing the size of the average filter, we are altering the amount of smoothing we are doing in the frequency domain. So this is going to get narrower, we are removing more and more high frequencies, a good thing in terms of noise, not a good thing in terms of actual real information frequencies, right, image frequencies. And as a result, we get a lot more blurring. Okay. All right, any questions on any of this? All right, so we'll stop here, I guess, pick up next class. Quick couple things.